Hello everyone. So in this video, we're going to quickly talk about CGSynth. CGSynth is a demo in Silicon this year. It's basically an extension from another work called CG Replay that was presented in NetSoft this year. So CG Replay is a platform that allows us to replay game sessions from cloud gaming sessions. Okay, so we have synchronization files for the commands that the user uh, did, okay, and the frames related to these commands, okay. So if I'm playing, let's say, Fortnite, I am using a joystick, I can capture these commands and I can send this information to a server. So you have the player side and then you send this to a server, and the server knows beforehand the frames. It has information of the frames and send the frames, the respective frames according to the synchronized commands, okay? And both sides are synchronized all the time. So why do we do this? Because existing tools for cloud gaming are quite limited in terms of reproducibility, because cloud gaming in general, like gaming in general, is not reproducible because it's non-deterministic. We never know what is going to happen in a specific scene of the game, and the user might have a different behavior under similar circumstances. Okay, so in this way, we created this platform, CG Replay, to support to foster the reproducibility of research on top of this topic. Okay, and then CGSynth allows us to try to extend this data set of any data set of cloud gaming sessions. Okay, so instead of collecting a lot of data, um we could try to manipulate these frames and see what happens. Okay, so basically we have three blocks here. The first one is the configuration. In this part of the architecture, we have synchronization YAML file. Sorry, for instance, let me show you config here. So this is an example of a configuration file, and we have the server IP. Okay. So what's the server? In this scenario, we are considering Mininet, okay, but it also supports Tofino. But for simplicity, we are going to show only Mininet, okay. So we have the server IP, the port, all of these network commands, and the network interface, and also we have the rate control, the server, the log server, and the log frame. Okay, and in the gamer side, at the gamer side, we have the IP again, the same thing. We can choose between three games to watch the game session and generate pcaps and extract frames from these pcaps. These are some of the features we have. So for now, we have Mortal Kombat 11, Fortnite, and Forza Horizon 5. Okay, we consider for now the encoding is H.264. We set the frame rate, the target frame rate at 30 FPS, and the max resolution we are able to generate using Mininet in a single computer, at least the ones we tried. The configuration, the hardware configuration we have is 1600 by 900. Okay. Also, we have a scaling bit rate because we also leverage a GStreamer. We started the bit rate at 5,000, and then we have a range. So the minimum value it can achieve is 1,000, and the maximum is 10,000. So we have more flexibility. Okay, let me see. So we also have some arc frequency, and this is how the synchronization behavior goes. Okay. And then now on the running section, we actually choose the game we want to replay. And this case is Fortnite. We are going to play this for 300 seconds, which means some seconds, okay? And we're going to stop at the frame 100, okay? So it doesn't matter if we play 100 frames before this time, it's going to last less than 300, okay? In this case, it's going to last for around 4 seconds, okay? Because the frame rate is 30. Also, we support the screen Scream is a congestion control protocol developed by Ericsson. But for the sake of the experiments and the demonstration, we just deactivate this for simplicity, okay? Okay, let me show you how to actually run it. So one thing we need is Mininet. We need to activate Mininet first. So the Python 3 Mininet examples. So we did not create a Mininet script for now, so we need to do this manually for now. Let me create a simple connection. At least the good side is you can visually see what is the architecture. Okay, so we will rename this for CG server. This is the server, and this is simulating the player. Okay, so we selected. Also, you can change the link properties. If we don't say anything, let's say it's 10 megabit. Let's say we have 1% loss, and that's it. Okay, in one of the links. So you're going to see this affects the quality of the frames, okay, when they are sent over GStreamer because we have some loss. Okay, let's run it, and then we can open a terminal. I need to activate the virtual environment that we created. This is the details of these instructions are on the GitHub. We have a wiki page there. Okay. And we go to the player folder. We just run the player first. It's going to pop up an error because in my specific laptop, I don't have support for for OpenCV with GStreamer because I think the version I was using only works on Ubuntu 24 and mine is 22, if I remind. Yes. So let me see. Let's go to the server folder in this case, and we can run the server, and we are going to send the frames. And you can see these numbers increasing because it's the number of packets being captured. Okay, and once we finish sending the 100 frames, we can just Control-C on the player terminal, and we created this file mypcap. Okay, where is it? Oh, right here. Okay, so we generated pcap from that experiment. Wait a second, I got lost here. Okay. Okay, so what can we do with this pcap? If you want to have a look, let me open folder then. You can try to use Wireshark. Okay, you can see. Let me see. So this is a single connection gameplay because we have the player and the destination is the server, or vice versa. I don't remember. Anyways, we can reconstruct this. Okay, so this is basically UDP, but if I encode these, we can encode this as RTP because it's actually RTP. The code as RTP. Okay, so as you can see, this is actually our RTP flow. We can see the information over here. You can see it's decoded as RTP. We can see the information here and the payload. Okay, and from this payload, we can, for instance, extract the frames. So we have some tools for this. Python, let me see, frame extractor. I remember how to use this. Because I need to search. Frame extractor. Okay, the video path. The video path is sorry. The frame extractor. Oh, no. Let's try another script first. So one thing we can do first is, let's see, extract MP4 from pcap. Yes. So there is two ways to do this. One, we can look at the pcap and try to mimic how GStreamer would display the video and extract the video that GStreamer is reproducing on top of the frames capture. Because if we have some loss information, GStreamer is going to try to interpolate the frames Okay, and if we capture directly from the pcap, we are going to see more greenish blocks. The missing part of the frame is going to be basically a green block because there is no information there. Okay, so first thing we can do is we can watch the pickup. This is another script. We have many scripts. Okay, why is displaying a lot of videos? Because it's reading all the pcaps from this folder. Okay, for now. So we can, if we place this pcap there, it's going to read all the frame. Later I can just add a flag that allows me to provide a specific folder for a single pcap so we can reproduce this guy, or we can just rename this for now. Let's say before backup, and this guy here is going to be empty, deleted. Yes, for the sake of the demonstration. Okay, so in this case I only displayed one video. Is the video you can see here, because it's reading from this path. Okay, what else? Output videos. Yeah, all the videos we created from previous experiment. And so another thing we can see is to extract MP4 directly from GStreamer. Okay, so let me, this is manual nail assembly, reassembly. So we can go to this script called RTP pcap video extracted. We can read from the folder output. Oh my god, output pcaps, and get the video, get the pcap called my pcap, and output right in the same folder. Let's say pcap, my pcap mp4, and the encoder is 264. Okay, you see, since we have a 1% loss rate, we have some corrupted frames. So let me see. In this case we generated, oh my god, it's not working. Wait a second. Output pcap, my pic mp4. Yes. So this is a video extracted directly from the pcap, okay, without GStreamer. So let's go to the next one, and I'm going to skip this one, but if you want, you can do this. We can extract the frames now. If you want to do like a frame level analysis, we can do this. So we can use the script. This script is RTP, no, extract frames. Actually, extract RTP frame. RTP frame extractor. Input should be the video, in this case. Yes, the video should be output pcap, my pcap.mp4. Output should be output pcap. Output frames actually. Demo. What? FPS 30. Something is missing here. Input is, input does not exist. Okay, so we have the frames. Okay, we can see now all the frames extracted from the video. If you want to do frame analysis, for instance, if you want to generate plots with this, you can compare frame by frame. We actually did something similar because we have this script align loss comparison, and we provide the frames, each frame. Okay, we compare frame by frame, basically. So after that, we can see some. This is just some evaluation we had so far. Okay, so for the sake of demonstration, we set the bandwidth for 4 megabit per second, the throughput, okay, and we set the loss at 0%, and in another scenario we set the loss to 1% to see how it behaves. Okay, so when we compare frame by frame, each dot here is a single frame. When there is a line, is because the frame is missing. The frames in these regions are missing. You can see there is a different amount of frames here. Okay, but the thing is, the darker blue and the darker yellow, the darker green of the games. Also, Combat is the green one, the Fortnite and Forza is the blue. They are the versions, they are the execution with 0% loss. And as we increase the loss, the VMAF is a metric created from Netflix. Okay, they have this metric, they have a paper on that, and also you need to have FFmpeg with VMAF support. This is also on the instructions from the wiki page we have on GitHub. So basically, these metrics go from 0 to 100, and the higher the better, basically. So you can see when we have a 0% loss, the quality, this quality is compared to the reference video. So we have a reference frame, which is the best quality frame, and we compare the videos running through a mininet architecture at 0% loss with 4 megabit throughput. When we compare the best video quality with this condition, we have more or less 84, 82, and 78% of similarity. And when we increase the loss, we decrease the quality, so we have more lossy frames. This behavior is more like little stairs and is quite unpredictable. That's what's happening. Okay. Also, this is a more detailed some metrics we have here. In this case, we are seeing the PSNR. So the higher the better. The dark blue is again 0% loss, and the light blue is 1% loss. So the higher the better. We have what we want here. Again, the higher the better for SSIM. And LPIPS is a model that tries to mimic how the eye, the human eye, perceives quality. And so in this case, the lower the better, and we have 0% loss lower than the 1%. And again, VMAF. Okay, we have this for each game, and you can see these results if you want on GitHub. So yeah, basically that's it for now.